Hey kids, let's do our last unit or section of chapter 15, where we're going to start this with linking some of the conversions that we've done in the last couple of sections with how to kind of do a conversion in a more general sense. So think about things we've done even back in Calc 1, where we actually did a conversion from a single variable in terms of x to a single variable equation in terms of u. And then in double integrals, we converted from a multivariable equation in terms of x and y into a multivariable equation in terms of r and theta. And then even in 3D, we basically took the idea of polar in 2D into cylindrical 3D and 3D spherical. But for each kind of transformation or conversion, we needed to pay the price, right? Remember to pay the price. So I think you remember what price, or we highlighted certainly the price that you needed to pay when you were converting to polars, converting to cylindrical or spherical. But maybe you don't remember that you did pay a price when we were doing U substitution. For instance, a typical U substitution in single variable calculus might have been something like 3x plus 2 to the 7th dx would have said, oh, I don't want to expand 3x plus 2 7 times. Let's pretend I did this from x equals 0 to x equals 1. Well, if we transform this x equation into a u equation, that's much easier to integrate, right? So you said, well, u is equal to 3x plus 2. So there was your u and then both of them to the 7th, but you couldn't just do the region you were integrating over. Didn't directly translate from dx to du, right? You had to say, well, if ux was equal to 3x plus 2, du was equal to 3 dx, which meant that 1/3 du was actually equal to dx, right? That was the price to pay for transforming from x to u. And then we did the same thing with our bounds. We said, well, when x is equal to 0, u would be equal to 2. When x is equal to 1, u would be equal to 5. And we did the same thing with polars, right? With polars, so well, if we're trying to integrate a function in x, y over dx dy or dy dx, didn't really matter, and I wanted to transform because either the integrand and the bounds were messier, I wanted to integrate this in terms of polars, where I would x is equal to r cosine theta, y is equal to r sine theta. I couldn't just change the region I was integrating over into dr d theta. What did I have to do? I had a price to pay. That price to pay was multiplying by that extra r, right? And then I also had to change my bounds from x and y bounds into r and theta bounds. And the same thing in 3D. So I want to focus on changing this region, right? Converting the region we're integrating to make integration easier and or possible. So in the region that I'm talking about is the domain region in the XY plane. We're going to take equations that are written in terms of x and y and transform them so that they contain u and v. We're going to call those equations transformations from the xy plane to the uv plane. And the new region is going to be called the image. typically, right, it doesn't have to be, but typically the region in the XY plane is called R or sometimes D. And the points, of course, have the coordinates, and so do the equations, X and Y. The new region, the image, is called S, where the coordinates in the equation are in U and V. But to go from XY to UV, there's a price to pay. What is that price to pay for going from the XY coordinate system to the UV instead of going to the polar system or the cylindrical system or from the spherical system? What's the price we have to pay to going to the UV system? So before we talk about integration at all, I just want to give you a region in the XY plane. So imagine this region is your domain that you're going to integrate over. So the points in my domain are X comma Y. They're all in here. I'm going to have some function, right, that if I eventually do want to integrate, I'm going to have an integrand, takes the XY points from that yellow domain region up into a Z space, and then we can use the double integral to find the volume between that first surface and Z space and all these points that we took from our domain. But when you look at our domain region, notice that I have two parallel diagonal lines that form two of the boundaries, and then two horizontal lines that form the horizontal boundaries. So if I write both of the diagonal lines down, notice that they both have a slope of 1. So if I rearrange these equations so that I only have a constant on one side, and actually I'm going to go ahead and multiply everybody by -1, just so I lead with a positive. If I transform X minus Y into U, notice that I now have two equations that represent two boundaries in my domain region as U equals 1 and U equals 2. Let's do the same thing with the horizontal equations. Both of these equations have a slope of 0. But I've got Y equals 1 and Y equals 2, the same variable. What if I let V equal Y? Then all of a sudden I have V equals 1 and V equals 2. So I have equations that transform, that rename X and Y in terms of U and V. And when I do that, look at my space. No longer in the XY plane, but in the UV plane. I now call this image S, where all the points in there are U comma V, and my bounds are vertical and horizontal, but defined in terms of U and V. This is really nice situation if we always liked integrating over a rectangular region because our bounds were all constants, which opened up nice possibilities for integrating, as opposed to having bounds that were determined by equations with variables in them instead of just constants. The problem is that the area of this parallelogram, though, is not the same as the area of that rectangle. But we have a way of finding the scalar multiple that does make them the same. And that scalar is the price you pay from taking a region that is not rectangular and transforming it into one that is rectangular. That scalar is the price to pay. Now, your book does a nice job of taking you through why this scalar turns out to be what it is, but I'm just going to briefly say that if you have a parallelogram, it's a terrible parallelogram, by the way, and on one side, and you have a rectangle on the other side, the area of a rectangle, right? Not a big deal to realize you just have a product of your length times your width. But of a parallelogram, do you remember if we made one side, talked about this being a vector versus another vector, just chapter, I don't know, was it chapter 12? We talked about the area of a parallelogram. How you find the area of a parallelogram is with a cross product. And if I talk about the lengths of these little teeny areas, not the whole area, because remember, we're doing little teeny areas in these regions of this small change in U compared to a small change in V, of all these little, as I move from a certain point. Well, in a parallelogram, if I have each of these, if I'm transforming my Y's and my V's is in terms of X and Y, my X is in terms of U and V. Sorry, I said X and Y, I meant U and V. Then the small changes are going to be differentials. So the cross product, the area of this parallelogram, which is a cross product, is going to be made up of differentials. And finding a cross product takes determinant work. So the scalar, the price we pay from going from the XY plane to the UV plane, is a determinant, and that determinant has a special name, and it is called the Jacobian, after the German mathematician that came up with this, whose last name is Jacob. I don't know how to say it, but that's his last name. But the Jacobian is a determinant. It is the area scalar, and it involves the partial derivatives of the transformations. There he is, Carl, I think is his first name. But Jacobian came up with the price we pay from going from the XY plane into the UV plane. Here's your determinant. Notice your determinant is made up of partial derivatives. As a result of an X equation in terms of UV and a Y equation in terms of UV, U and V. And of course, determinant work, remember, is the product of the main diagonal minus the product of the minor diagonal. And because we are dealing with area, right, area scalars, we are going to take the absolute value of the Jacobian. If the Jacobian ends up being negative, we will take the absolute value when we actually use it in our integral. And it gives the scalar, the ratio of the area of that parallelogram in the XY plane to that of the square in the UV plane. Crazy, right? So let's try one. Well, first let me tell you, to evaluate a double integral where we want to integrate a function in terms of X and Y, and maybe this integrand, is devastating to integrate in, as it is with dx and dy, or dy and dx, or maybe it's the bounds that are devastating. But we want to create a transformation that takes X into a function in terms of U and V, as well as Y in terms of u and v. And we're going to transform our integration over the region R into an integral over the region S. So again, x needs to be written in terms of u and v. Y needs to be written in terms of u and v. dA needs to be now in terms of du dv, but also with the price to pay for transforming from the rectangular xy region in rectangular xy to rectangular uv. And the Jacobian is the price that we pay. Those are absolute value bars. So let's start example 2. I'm gonna spend a lot of time on example 2, and I'm gonna at first just break it up into what does this region R look like before we start to talk about integration. So I want you to find the transformations that would define a new region, but in a UV plane. So the first thing I'm going to do is say, well, what does R look like? This equation is actually, right, if you get y by itself, this is y is equal to 1/2 x. This equation is parallel. The slope is 1/2. But with a y-intercept of 2. And then what about these equations? These are also parallel, right? So if you look at the region there, right, that region is bounded by 2 sets of parallel lines that are not vertical and not horizontal. I really would like them to be vertical and horizontal. So what transformations can I create to take these lines in the xy plane into the UV plane? So this one's not so bad because I don't have to do any rearranging. Can you see that? What if I define x minus 2y to be u? Who should I let v be? So can you see that u would then be equal to 0 and u would be equal to -4? V would be equal to 4. V would be equal to 1. Look at the region I now have. Horizontal and vertical lines. How much, as a domain region, who would you rather have? I hope you can see that this region S is more desirable than this region R as a region to integrate over. I've got a bunch of constants here. So now what I need to say is, well, if I want to integrate an integrand of 3xy over that region R, the same region that I just was given, this region R, here's my integrand, here's my region of integration. I want to transform that into integrating over the S region. So I've still got my 3, but X now needs to be written in terms of U and V, and then I need to multiply that times Y, which also needs to be written in terms of U and V. Well, I've got U in terms of X and Y and V in terms of X and Y, so I just need to now get these, right? I need to get X equals, right, in terms of UV, so get rid of Y, and then I need to get this, do the same thing and get rid of X. So let's eliminate Y first. So to eliminate Y, I'm going to multiply everybody by 2. I'm going to get U plus 2V. If I add these together, is equal to 3x. So x is going to be 1/3 u plus 2v. That's what's going to go right here. Now I want to do the same thing. Crap, I didn't want to erase all of that. X is equal to 1/3 u plus 2v. And then up here, and then I was going to do the same thing to eliminate x. So to eliminate x, I think I can just subtract, right? U minus v is equal to x minus x. Negative 2 minus y would be negative 3y. So y is equal to negative 1/3 u minus v. That's going to be right here. So I created the transformation equations. Then I got an x equals and a y equals. And now then I transform my space dy dx into du dv, but I have a price to pay, right? What's the price I pay? Who is it? Yep, it's Carl. Come on, Carl, let's go to work. So my Jacobian is a determinant of my partials. So partial x, partial u. Partial x, partial v. Partial y, partial u, partial u. Partial y, partial v. Do the determinant work. One third was positive, so I don't have to worry about taking the absolute value. That's the price to pay for transforming from xy to uv. That's the Jacobian. And then our bounds, what were our bounds? Remember our bounds from before, right? U is equal to 0. U is equal to -4. I put my du first. And v was equal to 4. V was equal to 1. Oops, sorry, -4. So my -4 should go here. Sorry about that. This 3 and 1/3 will cancel out. You have to multiply those through. Do that integration. You should get 164/9. Woohoo! Look at this one. You don't have to come up with the transformation equations. The transformation equations were given. And I want you to change from xy with transformation equations into r and theta, which means you have to transform your dx dy region of integration into dr and d theta. So if we think about the Jacobian for this, the price to pay for going to from xy into r theta is determinants by Jacobian. And we do our determinant work, taking partials of x and partials of y with respect to r and theta. OMG. See what we get there? Right, that's going to be negative is a plus. Factor out the r. Cosine squared plus sine squared is equal to 1. What? We knew this already. The price to pay for going from rectangular coordinates to polar coordinates was a Jacobian. We just didn't call it a Jacobian, but it is a Jacobian factor, right? Your scalar of going from one xy plane to the r theta plane. Crazy, right? Whoa. All right. This time, for this example, I just want you to practice getting me the Jacobian. Again, your transformation equations are given. If your transformation equations are given, and they are just asking you for the Jacobian, right? The area scalar. You're looking for your partials in x, partial x, partial u, partial x, partial v. Now your partials with y, partial u, partial y, partial v. Do your determinant work. This time the Jacobian was negative. So this is the Jacobian, but to use it as a scalar, right? Our area scalar, we would need to take the absolute value of that and get 5. All right, let's go all the way through a problem where I am giving you an integrand of x plus y, which doesn't seem devastating. And I want you to integrate over a region, dx dy, where the region has vertices in the xy plane, 1, 2, 3, 4, and I'm giving you the transformations equations. You do not have to come up with them yourselves. So the first thing I'm going to do is sketch and get the equations in the xy plane. So 0, 0, 5, 0, 2.5, 2.5, 2.5, negative 2.5. And then I drew those 4 lines and wrote the equations of the bounds, noticing that I have a set of parallel equations with a slope of 1, y equals x minus 5. And then I have a second set of parallel equations whose slope is negative 1. And again, I just used, right, the point slope form of a line, wrote those equations. So I have 2 sets of equations, and I am looking for that pattern where I have 2 sets of parallel lines. Since my transformation equations were given to me, x is equal to 2u plus 3v, and y is equal to 2u minus 3v, I can just go straight ahead to get my new bounds, right? Because I'm just going to take each one of these equations, y equals x, and replace them with u and v equations. Well, my animations didn't take now, did they? So let's start off with y equals x. Y is equal to x. And I was able to get the bound v equals w. Then I went to the other equation that had a slope of 1, y equals x minus 5. So now I have my 2 v bounds. So here is my xy plane, here is my uv plane. I just got v is equal to 0, and v is equal to 5/6. Then I went to my 2 equations with a slope of negative 1. Y is equal to negative x plus 5, and y is equal to negative x. And I got bounds again of 0 and 5/4 for u. So first region, here was the region in the XY plane. Notice that that region would have been whether I drew vertical strips and I tried to integrate that, look at how often my bounds would change, or even if I drew horizontal strips, right? My bounds would change as soon as I went below the x-axis. But here I can draw either vertical strips or horizontal strips, and my bounds don't change. Yay! So now that I have gotten my bounds, next I need to pay the price. What's my Jacobian? What's the price to pay for taking that parallelogram, right? And that area of that parallelogram in the 2D space going into the 2D space with a square in the UV space, right? The price to pay of going from XY to UV is a determinant of partials. So remember I had X was equal to 2u plus 3v, and y was equal to 2u minus 3v. So partial x partial u was 2, partial x partial v was 3, partial y partial u was 2, partial y partial v was -3. Did my determinant work? -6 minus 6, I got -12. Set up my integral. So the original integral had an integrand of x plus y. I had to transform that x plus y. I had to take dx dy or dy dx and transform it into du dv or dv du. And I had to pay the price. Remember my Jacobian, right? The determinant work was -12, but since we're doing area, we take the absolute value of -12. And then my bounds. Since I put du first, here are my u bounds. U equals 0, u equals 5/4, and here are my v bounds. V equals 0 and v equals 5/6. So I'm going to clean this up. I can put my 12 on the outside, just like we used to do in Calc 1, right? I can take 12, put it on the outside, or leave it inside. 2u plus 2u is 4u. 3v and -3v is going to go away. Bam. So 4u times the absolute value of -12 is 48u. Integrate 48u, I get 24u squared, evaluated at 0 and 5/4. That left me with 75 over 2 dv. Integrate 75 2 dv, and I get 75 halves v, evaluated at 5, 6, and 0. And I got 125 over 4 when I was done. Woohoo! So what we've learned to do is if we want to integrate in rectangular space, a region R, and either our integrand makes us sad, or our region makes us sad. or both. I can transform this into a region S that makes me happier. I'm going to go to transform dx dy or dy dx into du dv or dv du. My function, my integrand, are now going to be in terms of x is going to be in terms of uv, and y is going to be in terms of u and v. But in order to transform that area, I need the scalar to transform the area of that parallelogram into the area of the square. And the price to pay is the Jacobian. And remember, the Jacobian comes from determinate work of partials. And you want to take the absolute value of this. You want to positize that answer. All right, so again, this works when we've got a very, it doesn't have to be this, trapezoidal parallelogram-ish shape. We can do this. It doesn't really matter. This is a generalization. As long as you can get transformation equations and find their partials, you can use this technique. So we're going to stay just in 2D for the homework tonight, and then we will move to 3D when we do our second day of work with this. And one of your equations shows how to go to polars, so I want to do an example like that, where you, in your homework, where after you set up the, do the transformation, then you have to do another transformation into polars to make the integrand something that is easy for you to do. All right, so have fun with that, and I will see you at our next live session.